Can you hear me?
Yes, sir. Yes, sir.
Okay, great. Let me share the slide to see if it is working fine. Is it okay?
Sure, sir. Sure, sir.
So what do you see now? Is it okay? Can you see the screen?
Yes, yes, sir. It is visible.
Okay, great. Awesome. Good.
Good morning, everyone, and welcome to the fourth day of our ATAL FTP. Today we have two engaging sessions lined up, promising to expand our knowledge on advanced topic in high performance computing. The first session will be delivered by Professor Himanshu Thapliyal, who will speak on quantum computing circuits and design automation. Professor Thapliyal, a renowned researcher in quantum computing and VLSI design, will provide valuable insight into this cutting edge. Our second session will be delivered by Professor Rajesh Tripathi, will present on FPGA-based biomedical signal processing and its AI/ML approach. This session will highlight innovative way to leverage the FPGA technology for biomedical application, integrating AI and ML techniques. Now, I welcome Professor uh, Himanshu Thapliyal. Professor Thapliyal is currently an associate professor at the University of Tennessee, Knoxville, USA. He completed his PhD in computer science and engineering from the University of South Florida, Tampa in 2011, where he received the Distinguished Graduate Achievement Award. Professor Thapliyal's remarkable contribution to the field of computers, hardware and architecture are globally recognized. He was ranked among the top 30 scientists worldwide in the domain for 2022, as per the Stanford dataset. His accolades includes the 2019 NS Career Award and 2020 IEEE CSTC VLSI Mid-Career Research Achievement Award and the 2022 IEEE Computer Science Distinguished Contributor Award. With over 200 publications, more than 7,200 citations and an H index of 51 and 3 US patent, Professor Thapliyal has significantly advanced the field of quantum computing, VLSI, and emerging technologies. His research excellence has been acknowledged with Best Paper and Poster Award at leading conferences such as ISVLSI, ICCE, GLS, and others. He has also contributed to the global research community by serving as a general co-chair for major conferences including IEEE Computer Society, VLSI, ISVLSI, and SCM Great Lakes Symposium on VLSI. In addition, he is a member of the steering committee of IEEE ISVLSI and SCM GLS VLSI. A pioneer in quantum computing, Professor Thapliyal has edited a Springer book on quantum computing circuit system and automation and application. He co-founded the annual IEEE International Workshop on Quantum Computing and served as a track chair for the Quantum Computing track at the 2025 Design Automation Conference DAC. He is also a section editor-in-chief for Springer Nature Computer Science leading section on quantum computing and emerging technology and emerging trends in sensor IoT smart system. We are privileged to have Professor Himanshu Thapliyal with us today to deliver a lecture on quantum computing circuits and design automation. Please join me in warmly welcome him. Welcome, sir.
Okay. Thank you, Dr. Amit Panda. Thank you for your nice introduction. I hope that all of you can hear me. And I will share my slides and then we will continue from there. So just give me a minute. Okay. So okay, so I think all of you can see my slides, so I will start. Myself, Himanshu Thapliyal, as like Professor Panda has introduced actually. So currently I am at University of Tennessee, Knoxville, and my research groups has over a period of time has worked also in the classical systems, like we have been exploring like hardware security research, especially with emerging technologies, developing some solutions. And then we also work on some of the smart healthcare aspect. Actually, that is another research area. And over a period of time, we, as like Professor Panda has explained, that so my research group is actively involved in quantum computing in different domains. And today's talk, I will give you some of our works that we have been working in our research group. And if you ask me, we have been doing a lot of work, so probably it will not be enough time to cover all of these things. So I will give you some of the highlights of some of the works, and then some of the information you can always found in the research publication that our research group has published. And I have also provided my email ID actually. And then you can also connect me with LinkedIn. Actually, I think the LinkedIn is another best option that I consider always, that it's a good way to connect. So you can connect me through LinkedIn also, actually, because when we organize various conferences and all those things, we usually post it through LinkedIn also, actually. So it's a good way to connect, actually. So let's start. And first, this slides give you a perspective of the quantum computing, and I'm pretty sure that many of you may be familiar, but we'll just start with something like starting with a basic idea. And so if you see this particular slide here, if you see the quantum computing, then classically you have, just give me a minute, I will enable the pointer for you so all of you can see it. Okay. So if you see classically, you have this 0 and the 1 classical bits, but in the quantum, because the quantum, you have the qubits, and the qubits can be anywhere between 0 and 1 because it can be in a state of superposition. So that distinguishes it from the classical computing. So this particular slide illustrates an idea where this is the qubit, the information is in a qubit, and we are representing this as you can say this is the representation of, assuming that the qubit is in a state of 0, or with B, assuming that the qubit is in a state of 1, right? And where A and B, that is the two terms, represent the probability amplitude that qubit is in a state of 0 and 1, where A square and B square represent that the probability qubit is in a state of 0 and 1. So if you see, if one of them is completely 1, then you can assume that the other will be 0. So the qubit will be in a state of 0 or in the state of 1, depending on that. But sometimes A and B are neither 0 and 1. So so in that case, you can see let's say the qubits are non-zero state. When the A and B are non-zero, then the qubit is in a state of superposition. So that distinguishes the quantum computing from the classical computing paradigm. And so another interesting property that quantum computing have is called the entanglement. And one interesting aspect of the entanglement is that, let's say if these two qubits are entangled with each other, okay, and so the interesting idea, if you measure one of them, and then if you measure one of them and you identify what is the value of B, so it will also, you will get also information about, let's say, the B, or if you measure B, then you will also get the information about A, because they're entangled with each other. So that is the entanglement, actually. Okay. Now over a period of time, now we will start with some. So now if you see the classical computing, in the classical computing, you implement some of the circuits with the help of some logic gates. Then similarly, the quantum computing has two types of computation that we can consider. So right now, the era that we are in right now is noisy in nature. So people look into NISQ called, so it is a term that people use. It is like NISQ, NISQ. It is called noisy intermediate scale quantum computing. That is the current era. And hopefully in the future, when these noisy systems will move towards the more error tolerant domain, then we'll look into the fault tolerant quantum computing. So here, these are some of the gates that we call it like the fault tolerant gate set is a Clifford plus D gate set. And the idea is that if you, with this gate set, some of these error correcting codes can work on these gates more efficiently. And among these gates, some gates are slightly more expensive than the other gates. For example, the cost of implementation of T gate is slightly higher, let's say, compared to this C naught gate. So then when people look into some of these domains, their objective is to minimize the number of T gates in a quantum circuit, actually. So that is, and then this is one such example. This is one example of the quantum gate called the Toffoli gate or the CC naught gate. If you see, this is the A, B, C, and this is the input A, this is the input output B, A output B, and the C is transformed to a function called ABX or C. So this bottom figure here shows the equivalent quantum gate representation of this CC NOT gate or Toffoli gate. If you see, it consists of a couple of Hadamard gate, couple of these T gates, and so that's the whole idea. Now, interestingly, I will take you from the basics and then we'll look into some advanced concept actually. So these are some of the papers that we published over a period of time actually. So let's consider that initially you want to perform a simple example of a quantum addition, because that's a very simple case that anybody can understand. So you are assuming that you want to add a number A. That number A is stored. Let's consider, if you remember that, if you talk about the classical bit, then you are considering, let's consider you have a 4-bit number, then you will consider it A0, A1, A2, A3, like that. So in this case, we are considering a n-bit system. So if you see, it is going from A0 to AN minus 1. Similarly, B0 to Bn minus 1. So you want to add these two numbers in a quantum sense. That's the whole idea. So you create some quantum registers in this case, and in this case you stored A in this inputs A0, A1 in this register, and this is your, whenever you are performing some addition, you are also having some carry bit, and this is you stored at a location, let's say A minus 1. And this is the ancilla bit called Z. Ancilla is something, to summarize ancilla bits, sometime in the quantum computations, you need some extra qubit to store your outputs, and that is being represented in this case as an ancilla called Z. So you want to add this idea, and the interesting aspect is you cannot look into the classical methods, because the classical methods, if you see, if you ask me, you can convert, you can go to any digital logic book and you can convert, design a quantum circuit of that. But what is the issue? The issue in these cases will occur that right now the quantum computings have limited number of qubits, and so you want to minimize the number of qubit, number of logic gates. So converting just the classical circuit into a quantum circuit may not be a good idea. You need to look into the property of reversibilities and other factors to design it efficiently. So in this particular example, if you see, we created, this is the paper by, you can say, Kukar et al. So initially they create a majority function, and it consists of, you can say, a C naught gate and a C naught gate and a Toffoli gate, and implement a majority function, right? I hope that all of you remember that majority function. So this is one example that is being given to you. So let's say you have input Ci, Bi, and Ai. This majority function is going to generate for you in this particular output called Ci XOR AI, Pi XOR AI, and this is the Ci plus 1. So what is Ci plus 1? If you remember the majority function, what is the majority function? It is a majority of these three, right? Is the majority of these three. This means if either Ci or Bi is both 1, then the Ci plus 1 should be 1. So majority function can be represented as AB plus BC plus C or something like that, right? So this is the majority function, and because the quantum computing operate in a reversible sense, you also create an unmajority function here. And so this is the unmajority function. So if you cascade them together, a majority function with an unmajority function, then what you get, you have the Ci here, and this Bi, that is the initial one of the input Bi, get transformed to the sum, that is Si. So you're getting here A XOR B, I XOR Ci at this output, and this AI still get transformed to this one. So what do you get? What you get, like, this input remains finally after putting these gates together. This input still remain intact. This Bi get transformed to your sum output, and the AI still remains there, right? That's a simple example of addition in this case. So if you want to design like a bigger n qubit addition operations, this is one illustrative example. So what you do, this is an example of a ripple carry addition. So what you do, you cascade a set of majority logics here, and they are computing, and then you compute, and then you do the inverse of that one, because you have to, it is the idea of the reversibility. What is the idea of the reversibility? That you compute and then you decompute, so that you don't produce too many garbage outputs in this case. So you want to minimize the number of qubits also. So you compute, all functions you compute, and you do the reverse of that one, and then it's a V-shaped architecture you can see in this case. And what will happen because of that, again, as I discussed previously, that your input B0 get transformed to some output and this A0 like that. So what you're getting in the end is an example of a addition circuit, quantum addition circuit. So this S0 you generate at the input B0 finally, and the A0 is remain intact. And then the last qubit called the ancilla, we use it, and this ancilla we used to store for the last C out. Let's say if you perform some addition, then if you think in this case, if you perform an addition of a 4-bit number, then sometimes you have a carry out that is being generated. So you are going to store that carry out in this particular location called the ancilla location. So that's the sole idea. And then so over a period of time, what we looked into that hey, this is pretty cool, but can we optimize it further? And I will show to you recently my student has shown some of the applications. So during the time when I was I was doing my PhD in those days actually. So I thought actually maybe that design is interesting, but can we optimize it in a better way? So during those times, I proposed one of the adder architectures, optimized ripple carry architecture, and the sole idea is that we want to optimize the number of gates and all those things. And you recently will show through one of the demonstration that this circuit is more efficient in terms of noisy nature. So we propose this idea, and we if you see this idea is comparatively goes in this way. Our architecture also goes slightly in this way, but we try to minimize some of these correlations, some of the gates, something like that. So still it is the same type of operation, B0 to S0, A0 to like that, right? But the sole idea here, we want to optimize the number of gates actually, and so that's the circuit is slightly more optimized. Now, once this addition circuit is being done, then of course you can transform this circuit into, let's say, a control addition circuit. What is the control addition circuit does is that if you see this circuit can work as both as subtractor in this case. And so this particular example, if you think in this case, we are using this property, we can perform the operation of subtraction called B minus A by using this method, the complement of B plus A, and then you take the whole complement. That is one example of the subtraction operation, right? You are performing subtraction. Now you can also perform the addition subtraction, and in this case, we put a control bit here, and depending on if the control bit is 0, then you perform the addition operations, and if the control bit is 1, then this bit gets flipped, and so we are performing B minus A is equal to again B bar plus A. But if this bit is 0, then it doesn't get flipped actually. So in other words, if the control is high, then you are performing B minus A, but if the control is low, then it's just passing the bits and then you're performing the addition. So in this manner, you can perform a control, you can say addition or subtraction operation, right? Then interestingly, my PhD student, one of my PhD student, he's a faculty now in one of the universities in US. So he during his PhD time, one of my PhD student, he looked into this circuitry and he said, oh, maybe we can come out with a better optimized version. So here we looked into a different type of control addition. The previous one we are looking into addition and subtraction operations, but here the sole objective is to perform conditional addition. Here we are not performing subtraction. Here we are just performing, if the control bit is low, then you just perform pass through. In other words, the B will just come to S0, B1 will come to S1, B2 will come to S2. It will become a pass through. But if the control bit is high, then it is performing the addition. So it is called control addition in this case, right? So this is interestingly, and now I want to show to you where this will be deployed. So then again, one of my former PhD student in his PhD research, we looked into one of the quantum circuit for multiplication, and this work published in IEEE Transition on Computers. You can get the whole paper here. So what is the sole idea? If you're performing the multiplication operation, then the multiplication operation can be represented as A dot B is equal to like this operation. You can say A and B, and then depending on its weight, you're multiplying with 2i like that, right? So that is, so if you see in this case, you can call it like a shift and add based multiplication algorithm. The interesting idea, how can we convert this circuit to an equivalent quantum circuit? So you have to think slightly, because as I told you, our objective is to minimize the number of qubits and the number of gates. So in this paper, one of the papers, what we did, we first create, you can say, the control adder, and I showed to you already what is the control adder. This is the control operations. So in this case, it is performing the control addition, and this is a Toffoli set of arrays. So what is the interesting idea? This is a Toffoli gate, and this is a Toffoli set of arrays that is being designed. Now, so to perform this operation, let's say a dot bi dot ti and 2 bar I, and then you're performing, you can say that's the whole thing we want to generate. If you want to perform a, let's say a 4-bit multiplication, right? So you are performing a times b0, then plus time 20 plus a times b1, like that, right? So this is the whole architecture that is being shown here. So if you see in this case, these are the bit b0, b1, b2, b3, and this is my A3 bit. This is what it is here, and this is the ancilla lines that is initialized to 0, and then you put up set of Toffolis and the control additions. As I told you, your objective is to realize this function in an efficient way. So it is realizing this function in an efficient way. So what do you get in the end is this b0 remains such, but this operation, because it is going, this inputs b and a are going through a set of transformations here. So what do you get in the end is a product bit, let's say P0, P1, P2, P3, and these are the quantum multiplication that you get in the end, right? And you use only one ancilla line. So this is the example. I will not go into the gate counts, but the interesting idea is that now you can realize quantum additions with reduced number of qubits and reduced number of gate counts and all those things. I told you, if you want to go into look into more details, you can always look into the paper. The paper that I looked into that is this one actually. Okay, so that's pretty interesting. But now over the last few years, we thought, okay, let's focus also on the real quantum system, because so the real quantum systems right now are very noisy in nature. Because let's say if you take any of the quantum machine that is developed by companies, let's say any companies that is developing a superconducting quantum computing and all those things, they have a lot of noise. So what we thought, actually interestingly, how can we minimize the noise and also make the circuit work? Because so one interesting aspect I want to tell you, if you are performing some computation, right? If you so this graph is pretty useful for you to understand. So if you develop a circuit that will have a depth, higher depth. What is higher depth in this case? Is the delay. Okay, is the delay, higher delay. Or in other words, if you ask me if you ask me at the layman language, what it will mean, that let's say if you see my screen, if a qubit encounter more number of gates over its path, and that the qubit has to go through this transformation, then the circuit not working correctly is high, because the depth in this case is going to be very high, right? And then you are also putting a lot of gates around, right, the path. And because of that, what will happen? You have a long path, and the circuit will be noisy in nature, right? And because of the noisy nature, the circuit will not produce the correct output. That's a challenge in the quantum system, that how do you make sure that you develop a circuit which are, you can say, low depth. This means shorter delay, less number of gates. So what we thought in this case, why don't we use approximate computing for doing this problem actually? Okay, so we looked into this idea of approximate computing. And so what is approximate computing, by the way, right? And the sole idea we want to use is this approximate computing. So let me tell you what is approximate computing with an example actually. So what is an approximate computing? If you think in this case, let's say whenever you perform an addition operation, you want to always get an exact answer, right? But many applications, like say image processing or sometime signal processing type of applications, may not require, even the machine learning sometimes may not require an exact result. So you are fine with an approximate result. For example, let's say if you're watching a TV and you bought a TV that has 4K pixel, and you watch that in a HD TV or 2K pixel, it's difficult for human eyes to understand it's a 4K pixel or it's a 2K pixel system. So that idea has been widely used in the classical computing for developing low power systems over a period of time. Here we apply this domain into the quantum computing domain, but here objective was not not no low power. Our objective to use this approximate circuit and use this approximate circuit to reduce the noise, because we can eliminate some of the gates which are producing some noisy systems. So it can help us to develop some systems which are approximate in nature, but it is working more correctly than the exact version, right? That's the sole idea. We want to use approximate for reducing the noise and improving my circuit output. So this work we produce in GLS one example. So we propose, you can say, a couple of this approximate quantum adder, 3 with carry out and 2 without carry out. And we conducted noisy simulations to show this idea. And what are the noise sources? So whenever a quantum system perform, you can say right now, because these quantum systems are not stabilist in nature, so you will have a lot of different types of noise. For example, thermal noises, you have depolarizing noises. Whenever you perform like the state, there is state preparation errors. Whenever you read the system out, there is a readout error. There is bit flip error, that is the gate is gate flipping, spam, phase damping. So there are different types of errors, right? So our objective is that, let's say if you run a simulation of an exact circuit and now you run a simulation of an approximate circuit, which one will work better? So that's our hypothesis, is that approximate should work better, right? But now we need to test it, and now we need to come out with some sort of new ideas to what type of circuit we can design in an approximate way, right? So if you see these two adders I already showed to you. This is one of the adder that is proposed by Kokaro, right? Remember that I told you about the majority and unmajority logic, right? Majority and unmajority logic. This is the circuit, right? So it is the same circuit. But if you interestingly, if you see the circuit, once this qubit computes, then there is no computation happening after that. So this qubit is in idle state for a very, very, very long time, you know. And so the qubit is in idle state for a long time. Similarly, this MSB qubit is idling for a long, long time, and that can result in a noisy sources, because, as I told you, if you see this light, you have amplitude damping, right? The after some time the qubit will lose its state, phase damping. You have other types of errors, so we want to test it, right? So then, if you see, that is another adder that I showed to you, that is proposed by me actually in during my. So this is that TPL 13. That is one of the adders we proposed. Now, this is the depth comparison of the two adders, right? This is and this is exact version, not the approximate version, just to give you an idea. So this shows that, you know, the how this is exact adders which we compare with, right? So I think all of us are in the same page now. This is the exact quantum adders. Now we propose a set of approximate quantum adders. Now we propose a set of them, and if you see the first one, we just use a simple idea, and we thought, what could be the worst case problem that you can occur? The worst case is, or the best case that could be, there is no gate here. We just assume that when you're performing addition operation, we just assume that the sum bit is equal to one of the inputs. So we are just assuming this Si equal to Ai. We did not put any gate in between. So in other words, let's say you're performing an addition of A plus B. We are just saying sum is equal to A. We are not even bothered about B, because we want to test this circuit to see how much noise it is going to impact the output, right? Second case, this is the adder number 2. We just put a C0 gate. So now this circuit is going to perform. Initially, it was just doing S equal to A. So we also introduce a function called S equal to A XOR BI. But if you remember that, what is the exact output? The exact output is usually A XOR B times your carry input, right? These are XOR operations. So this is my exact output, and you see this is an approximate, and this is highly approximate in this case, right? And we are not assuming there is any input carry. So these are the two adders where we do not assume any input carry. But you see that even we don't assume there is input carry coming from somewhere, whenever you perform the addition, some input carry is going to generate from these stages in between, right? So you have to take care of that one. So this circuit is approximate because we are not even bothered about this carry that is being generated in these intermediate stages, right? We're just using the approximate one. So that's the case. And then the another case could be, let's assume that you have this again the pass-through circuit, and in this case, if you see, we are also generating this carry output, right? So we are generating this C out carry output, right? And so in this case, we are not generating the carry output. In this case, we are generating the carry output in this case. So we consider the function Si equal to this one again, and then we also put a set of Toffoli gate, right? So there are two functions that we are generating. One of them generate the C out, another one doesn't generate the C out, right? So that's the two functions that we looked into that. Now, these are the exact quantum adders, as I told you. These are the exact quantum adders. These are the functions, because you see, this will work accurately. It's completely correct. And this is the gate set, number of gates that you will require on this adder. Okay. Now, these are the proposed adders that is approximate in nature, right? So you see, this is the exact one equation. This is the approximate equation. We just approximated it. And you see, this is constant depth adder because you hardly have one or two gates in between. So that's why you see these gates have so many gate count, but our design has hardly 0 or 1 or maybe NC naught gate maximum. The depth is only 1 because there is no gate that we are encountering. So anytime the system sees it, is going to see only one gate irrespective of the circuit size. The depth is constant here. Or we can say this is an order 1 quantum addition. Okay, pretty interesting, right? Because instead of you looking into order n, we just make it order 1 approximate adder. And now let's put it into the simulation and see how does the noise impact it. So now if you see, this is the normal and this is the mathematical terms. Let's not worry about it. Let's look into the actual simulation. You can look into, these are the mathematical formulation to see if you perform an approximate addition, how much it is going to deviate from the exact output. So this is without simulation. This is the classical way to look into the let's say if you generate 0 0 0, what is my output, how much far it is from the exact output. So this is the mathematical analysis, but this is the actual noisy simulation. So now, as I discussed with you, we looked into different types of noises, right? Interestingly, you see this is the exact adders, and as soon as noise start coming into the picture, you think in this case, one, you consider the fidelity of 1 means your circuit is completely working fine. But in this case, the circuit is only working 0.7 times, 0.5 times. The circuit started degrading. It's not 1, right? It is less than 1. This means the noise has started impacting my output. And if it is an exact adder, if it is an approximate adder, of course it is impacting, but it's not impacting that much. You can see the difference between those two, right? And so what do we learn? So we learned that, yeah, the approximate adder is really started performing better compared to this exact adder when you consider the noise into picture. So you can see there's significant improvement into the approximate addition. In other words, the approximate addition is more reliable in the quantum systems when you're considering noise into picture. Okay, and that's the sole purpose here. What do you understand in this case? The spam is a state preparation, and the readout error impacts all adder uniformly. Interestingly, thermal and the bit flip errors exact adders more because they have more number of gates, right? So they have more number of gates, so it's impacting it more. But the approximate adder doesn't have that many gates, so it is impacting it less, right? So this is some examples. You can look into the if you can read this more paper, as I told you, this paper, if this is a Great Lakes Symposium paper, you should be able to find it from the ACM or from the archive. Actually, we should have posted in the archive also. But I think I'm able to convey you the idea that how the approximate computing is helping in this case, right? So what do we learn? That we learned that by using the approximate computing or the approximate quantum adder, you can design circuits which are fewer resources. They have the constant depth, and they have the carry generation mechanism is simple, and so they work it more reliably than the exact adder. Okay. Now this is pretty interesting. Let me see how much was the time. Okay. So now this is pretty good, but this method that we talked here, we are looking into designing this circuit with hand, right? Now, can we develop a tool? Because that's why we call it design automation, right? So can we develop a tool that I don't have to design many of this quantum approximate circuit in a manual way. I can use a tool for doing that. And so I have a PhD student here working with me. His name is Joseph Clark. So his thesis is on design automation of these tools actually. So that's what he's doing actually. So this is the whole flow. So what happened in this case, if you see, this is the design automation quantum approximate synthesis tool. So you have the initial circuit. It could be some sort of Boolean mapping, and your job is you want to create an approximate version of that one, right? In the step one, you map the circuit to a hardware using the Saber. This is the tool that is available through the biscuit. So then this is you map this thing, and then after that you partition them. Partition is, if you remember the classical VLSI design, you also partition them because you have a big circuit, then you partition them, and then you accordingly play with that circuit, right? Because once you have the partition, you can do a better job with that, because you're now dealing with not a big circuit, you're dealing with smaller sub circuits. So what you do in this case, you take a big circuit, you map it in terms of qubits. Now it's mapped. Now you partition them into small blocks, right? And I will briefly talk to you about the partition algorithm that my research group has proposed. So you partition them. So now it might be possible that you created, let's say, this is the original circuit. You created different partitions, smaller block of the circuit. Now, each of these blocks, let's say, or in block one, block two, you can create different approximate version of this one, as I showed to you in the previous. Let's say I showed to you that you can come out with different addition circuits. Similarly, this can be any circuit, a block one. Then this means then different variant of this circuit could be created. So we are calling it block one, approximate one. Like so, we are calling it. Let's consider that n different blocks can be created. Similarly, for the block number two, different variation can be created. And this is only not block one and two, there could be more blocks, right? Now, so you have created an approximate version, and now you recombine them. When you recombine them, then it might be possible that I choose block one from here, maybe block for the block two, I choose this is the better. And so we are just combining them, and then we are creating different approximate version of that exact circuit. And then your objective is to identify which one of them is better, which one of them works better in quantum computing, because you have the different types of partitions, right? So this is the tool flow called quantum approximate synthesis tool flow. Okay. So my research group, over a period of time, one of my, as I told you, Joseph Clark, one of my PhD student, became the partitioning algorithm. So here we consider that, let's consider a n qubit circuit. You have n qubit circuit and with g number of gates, and then you partition them into a minimum number of sub-circuit B, such that each sub-circuit contain a maximum number of k qubits. So you want to create a partition algorithm. And the reason why I want to create a partition algorithm, because once you partition that, the synthesis become much more efficient, because it takes, if you see the synthesis operation means taking these circuits and converting them into gates and all those things, mapping them. So it is order of exponential time, but if you do the partitioning, the runtime becomes lesser. So that's the sole objective of the partitioning. These are the existing partitioning methods that is proposed. So there is a tool called Bqiskit. You can see it is on the Berkeley National Lab, Lawrence Berkeley National Lab. So here there are two algorithms that are available for the partitioning. One of them is called quick partitioner, another is called the scan partitioner. And the quick partitioner is simple but fast, but it doesn't produce that good quality result. While the scan partitioner is slow, it is very exhaustive in nature, but produces good result. So what is the difference? That in the quick partitioner, it iterates over the circuit gates and group them into blocks and as their encounter, while the scan partitioner exhaustively tests all possible groups of interacting qubits to form each partition. So the scan partitioner is much more efficient than this quick partitioner, but it is very slower in nature. So we want to come out with a partitioning algorithms that is produce good quality results. This means good partitions, but it's not that slow. Okay, that's the sole objective. So this is one of the algorithm that we propose in I think in 2023 in one of the papers. GTQCP is called greedy topology quantum. You see this one, greedy topology aware quantum circuit partitioning algorithm. So this GTQCP partition, you can say an n qubit circuit with g gates into minimum number of sub-circuit with not more than qubits. And so that's the sole idea actually. So how does it does actually? It consists of a set of steps, and I will not go into too details in the interest of time, but just you can look into more details. But it consists of basically two steps. First, we do the dependency calculations, and then we create the group enumerations. Okay. And what is the dependency calculation means? That let's say you have this quantum circuit, and this is the set of qubits, And then you're creating a dependency graph that which gate is dependent on which number of qubits. So in this particular case, you can say that this particular gate here is dependent on the qubit number 0 and 1. So you're fighting at 0 and 1. This gate is dependent on 2 and 3. So you're creating a dependency calculation, like how do you do in a graph theory, right? Then after that, this is a dependency calculation you create, and then this is the whole idea. You see, this is a dependency calculation. Then you create a group enumeration. You want to limit the number of qubit, let's say 3 or 4, and you want to find maximum number of gates that can come within that group. So there's a group enumeration algorithm. We use it. And then once this algorithm is designed, we tested it on this set, and we put like, so our objective is k equal to 4 or 5. What does mean that? It means that we want to create partitions such that each partition can have maximum number of 4 qubits, or each partition can have maximum number of 5 qubits. And let's say there is a big circuit of 32 qubit or 64 qubit or 1000 qubit or 5000 qubit. You want to partition them into small blocks such that each partition can have maximum number of 4 qubits. That's the whole idea. So then we tested that in some of the benchmark circuits, right? And then you can see in this case, this is the GTQCP that we propose, and you can see its execution. This quick partitioner is the one which run very efficiently, but it produces bad quality result. But if you see in this case, our algorithm is running almost as close to the quick partitioner. So runtime is pretty good now. So that shows that the algorithm is almost working as efficiently as quick partition in terms of execution time. Now, how about the quality of the results? Now, that is the average number of gates per partition, right? So if you see in this case, again, GTQCP is as good as the best algorithm called scan partitioner. So what we are proving in this case that GTQCP produce as good quality result as scan partitioner and running as fast as the faster algorithms called the quick partitioner. That's the sole idea. And you can see in this is some example that we showed that how the GTQCP is improved compared to the scan and quick partition in terms of the quality of the results and how it is doing in terms of execution time. It's running very faster, and it's producing a really good quality result compared to the quick partitioner. Okay. And these are some big, surprisingly, some of this on the bigger benchmark circuits, some of these existing algorithms was taking long time to run. So that shows that. So in this case, if you see, sometime this graph, you see, the scan partition is taking long time because it is so slow in nature. Okay. So I won't go into all details, but you got the idea. So now, once this partitioning thing is done, we want to combine them. Okay. This is the combination step, and then we want to create a different version of this approximate. So we came out with different algorithms. First up is called cascaded error estimation. So we estimated error using pair of adjacent block rather than individual block. Second is the error fidelity evaluation. So we looked into different methods, and some of these methods we want. So if you see, what is our sole objective? Our sole objective, once this different partitions is done, we need to combine them and find a very good overall approximate circuit that is doing better than the exact circuit. This is the exact circuit. We want to create this one such that when you run in a quantum machine, this approximate circuit performs better when there's a noise in the quantum system. This approximate circuit behaves better than the exact version. That's the sole idea, right? So we look into these combinations. We look into this combination algorithms, and so we came out with this couple of methods. And so the sole idea what we did in this case is that, you see, so we came out with a couple of these methods, and the interesting idea we want to come out, and just I want to give you some insight because there's a lot of technical things to talk here, which will maybe like it will take 1 hour lecture just on this topic. So just to give you an idea, I will give you some idea of the error aware fidelity evaluation. So what do you do in the error aware fidelity evaluation? Let's first talk about cascade error estimation. So when cascade error estimation, what do you do? Let's say previously people were considering only, let's say this is the block, and you create an approximate version of this block. So you are not considering the other blocks into picture. You're not considering how this block is being connected to this one. So that was reducing the quality of the results. In our case, we looked into, let's say this is the B1 block. What is the dependency of the B1 block in other blocks? And then we consider it's called cascaded error estimation. this code all pairs of addition partitions, not the individual partition. In this case, that is the novelty in our algorithm, that we are also considering the error that is being occur, because the you can say none of the systems can behave in isolation. Something is always dependent on something. So that's what we're also considering, the errors that is accumulating together. Another thing that we'll also look into is error aware fidelity evaluation. In this case, when we run a system, we perform an idle simulation of the exact circuit, right? You have the exact circuit. Then we also perform an error simulation of the target hardware with approximate circuit. And then we want to, at each step, you have an exact circuit and an approximate circuit. We run on a simulation method, and then we compare how much this approximate circuit is behaving compared to the exact version, and we store them, and then we keep on storing them. And the end objective is that the overall accumulated error should be less than the exact. When you run an exact circuit, this means the exact circuit is impacted more by the noise compared to when you combine these circuits and run them in a quantum machine. So that's the whole idea of error aware fidelity evaluation. So interestingly, there's more into it, but to give you an idea, this is by using this method, what we showed that this methodology can give you better circuit compared to the approximate exact circuits, and compared to the existing literature, we show that our circuit is producing high quality result. This means our circuit can run it in a more better way, less impacted by the noise. So that's the sole idea. Okay. Now I will go to another interesting methodology, and you can look into all these are all papers, and you can look into that. So interestingly, see, in the classical literature, people have used the residue number system a lot. I think some of you have used the DSP system. So what happened in the residue number system is that you have this residue number system. If you see the previous system that we talked about, there's a dependency of the ripple carry addition. Like for example, a carry propagates like this, right? So there's a dependency in the residue number system. Each one of them can operate on parallel residue number systems. So in this case, this is a residue processor, one residue. So what is now the benefit in this case? If you take a number and convert into this RNS residue number system, this can operate independently, right? So consider that these are the parallel machines. One is running like this, one is running like this. So the impact of the noise of this one is not going to impact the noise to this one, because they are all operating in parallel. So what we use this method, we thought, hey, this residue number system is cool because they operate in different moduli. So this is an interesting example. So let's say this is a residue number system, and when you take this one of the moduli set, so you need a quantum modulator at 2n minus 1, quantum modulator at 2n, quantum. So this is, and then you perform this one you perform classically, okay, and this is the quantum operations. So interestingly, now you see in this case, this one is operating independently, this is operating independently, this is operating. So what you are doing, you are operating three parallel channels now, okay, and these parallel channels are operating independent of each other because there is no dependency between them. Since there is no dependency in that, this system can better tolerate the noise, okay. This system, each one of them can better tolerate the noise because we remove the dependency of the circuit, right? This means we make the system parallel rather than cascading in nature. If you do the cascading in nature, you're increasing the delay, and because of that your circuit is failing in the quantum machines. So we use this residue number system to make the circuit in parallel. So we tested this idea. What if you have, as I told you, like the adders that we already know, right? For example, this is one of the adders that I proposed in the past. If you run these adders, you see this adder is performing like this. But if you perform this residue number system that I told you, you see that compared to this adder, that is, and this is exact error. This is not an approximate error. I want to leave in the RNS. You see that circuit is really performing really cool. This means the residue number system is able to better tolerate the noise. This is one interesting example. If you have, this is the red color shows the classical way that people have performed the addition. This blue color shows that if we change the addition operation to the residue number system, and now you can see the residue number system, because it operates in parallel channel, it is better able to tolerate the noise. Okay. Okay. Very good. So we'll continue from here. And I think so. What we understand that this residue number system, which has been used in the classical cryptography and all those things, we used in quantum sense, and our objective was to develop a system which is noise resilience. And I showed to you that how do we can develop the noise resilience systems. Okay, and it's pretty useful idea actually. Now this is all good. Now I want to give you some other insights quickly, and then I will stop after that for Q&A. So another interesting thing, people have been looking into the idea of quantum machine learning. Okay, so my research group is also actively looking into quantum machine learning, and I will present one of the works to you to give an idea. So if you see the cyber physical system, right, this cyber physical system has couple of sensors and all those things, because all of I personally have worked a lot in classical cyber security, so I have a lot of projects that are funded through different agencies on this classical cyber security, specifically CPS security. So I thought, okay, this is really good. Can we use quantum for some applications here? So if you see, this is the CPS systems, and it has a lot of sensors. Somebody can attack the CPS systems, and they can attack the sensor, and the reading can change, and so it can do a lot of damages to the system, because some of these CPS systems are sometimes controlling your grids, sometimes they're controlling the, you can say, your autonomous systems. They are controlling sometimes your whole water system. Sometimes they're controlling the critical infrastructure. That's a big issue. This is an example of the attack that has happened in a CPS over a period of time. So you can say cyber physical systems are a lot of vulnerable to attacks, right? So we came out with this idea, and here this is a hybrid quantum system, where a part of the pipeline is classical and a part of the pipeline is quantum. So what we do in this case here, this is we train the data set with anomalies. This is all operation happen in a classical sense. This is a classical computing that is going on here. Okay. Now we pre-process it and do the feature selection. So we do the pre-process, and this pre-process feature selection happen in the classical world. Then you put this into this quantum system. Okay, this quantum system has this like feature encoding methods. And why we want to put in the quantum system? Because I will show to you an example. We want to put this data into high dimensional data, so that once you put into the one class SVM, the one class SVM can do the better prediction in this case. So one class SVM is again the classical, only this portion is quantum. So here, if you see with this circuit, this is again a set of the uh, the data set that we took. So we take this data set. It consists of 4 components, like the boilers, turbine, water treatment. A lot of data coming onto that, and we took the data set that has around 177 hours of the data training set. Then we have the test set. The test set at 38 attacks. This is the real world data set. This is not like a fake data set. This is the data set that people have used in the industries, and that is available online. So we use this data set. You can also look into that if you are looking into CPS security. And so our objective is to find the anomalies that is happening in this data set using the method of hybrid quantum classical methods, right? So then what we did, this is the portion that I told you. This is the feature encoding and this feature elevation kernel and the compute state between fidelities. This is the source circuit. So here you take this data that is coming. This is the feature selection. This is encoded. So because this is the quantum, so you create like the U function. You also create the inverse function. So the sole objective is that you feed the test like the train data. This is also like the similarly like a test data, and you want to see how much close they are actually, right? If the fidelity, ideally they should be very close, then so in other words, high fidelity means that the there is less anomalies, right? And if there is low fidelity, this means there is an anomaly. This means there's a difference between this data and this data, right? So we encode this into the qubits, and this is an example. So if you see this high fidelity and the low fidelity, this is the anomalous data actually here. Okay. So once we put this thing, so if you see, this is the classical SVM. In the classical SVM, this is hard to have the boundary. This is the anomalous data, and this is that you can say the normal data analysis are all accumulated together. So for the one class SVM, it is difficult to do the binary classification. Either it's anomalous data or it is a real, it's a normal data. But with the help of quantum, we are better do the you can say put in a higher dimension, and now you can say you have better segregation between this anomalous data and the normal data. You can say the quantum has able to spread this data in a better way. So it is easy for one class SVM to now do the binary classification in this case, right? So now this is the system now we use for quantum anomaly detection. So we, as I told you, we took 16 features, and each qubit is able to map two features. So 8 qubit means we are able to encode 16 features. If you have 16 qubit, then you're able to encode 32 features. So as I told you, we use classical methods to identify which are the best features. And compared to a classical system, assuming it is a 8 features or 16 or 24 feature, this is how the accuracy that we got in a classical methods. This is precision, this is the recall, and this is the FR score. If you use the quantum, hybrid quantum, I will not call it fully quantum because a hybrid quantum, because only we are using quantum just to put the data in a higher dimensional state. So if you see in this case, the accuracy of the system is almost this 74, this 86%, this precision is also increased. So what we are showing in this case that with the quantum kernel methods, it gives you higher F1 score and improve accuracy. While the classical system struggle with anomalies, quantum does a really good job. Okay, so that's the whole point. And before I stop, I want to give you one other interesting aspect that my research group have explored, that the idea of quantum transfer learning actually. Okay, so I will quickly briefly talk about this. All papers are available. If you search my name, you will find all these papers actually. Okay, so here we took a data set. Here we took an anomaly data set that is from the printing machines actually. So the sole objective was to identify the anomalies when these printers are printing these images actually. Okay, so we want to identify the images anomalies in this data. So we use quantum transfer learning. What is the quantum transfer learning does is, let's say you train a classical machine learning pipeline. So then once the model is trained, you got this one. Then some of the layers you replace by a quantum layer. So in other words, you have a trained model, and let's say it consists of, let's say, a 5 layers, and then out of these 5 layers, you keep 3 layers classical and the remaining 2 replaced by quantum. That's called a transfer learning based method. So we tried to hybridize this one, replacing some of the layers by classical layers by the quantum layers, and we want to see what is the benefit do we got. So in the quantum transfer learning based methods, we showed that this is the classical model, right? And it has a huge number of parameters, right? But if you use this quantum transfer learning in which a part of the layers are replaced by quantum layers, then you can see the number of parameters are significantly reduced, right? So in this case, the number of parameters are significantly reduced by a huge number, right? And similarly, in this case, you can see the number of parameters are significantly reduced, almost even by 90%. So what you can say that, and then interestingly, that the model is performing better compared to the classical methods, right? Okay, this is a classical method, and if you use this quantum transfer learning based method in which a portion of the layers of the classical machine learning you replace by quantum, then you started getting better results. So that's the sole idea. So what we want to convey to you that because interestingly, you can develop the full quantum systems, but right now it's also a good idea that you take the power of the classical machine learning, then merge with quantum ideas so that you create hybrid quantum classical solutions. And those quantum classical solutions can be implemented right now on the quantum system, because the quantum system has limited number of qubits, so you cannot run really very complex algorithms and all those things. So but you can take the power of classical system to identify the important features, then you can take those features and run a quantum machines, and those quantum machines are going to do a really good job for you. So in summary, we can say that that approximate computing has significant potential benefit to increase noise resilience of quantum system. I also talk about this RNS-based computer system that can help you to perform the things in parallel and develop the things which are better noise resilience. I showed you that how the hybrid approaches that utilize the power of classical and the classical machine learning along with quantum computations can give you better results. So I will stop here, and I will be happy to take any question that you may have.
Hello, sir.
Hi, Amit.
Uh-huh.
Yeah.
So, one second, sir. Participant, if you have any query, you can drop a message on the chat box. So anyone who wants, they can raise the hand also. Sir, there are questions coming from the chat box. So what is the major difference between quantum and neuromorphic computing?
See, the neuromorphic computing is a separate paradigm. Okay, neuromorphic computing is a separate paradigm. There, people are see the quantum. People are looking into some methods like quantum reservoir computing, but the neuromorphic computing, if you see, is mostly designed to mimic the ideas of the brain, so that you develop the low power system, right? But the quantum is a different, slightly different in that sense, because here you're looking into completely quantum properties to develop systems. So you're not caring really about the low power aspect right now. You want to really take the capabilities of the quantum system to perform better diagnosis, better predictions, better applications. So that's why it is different. The both domains are like different to each other.
Sir, one more question is coming from C. Pakiria. Can you give open source tool to perform quantum computing?
Yeah. So very good question. So if you see right now, IBM Qiskit is there. Okay, IBM Qiskit you can use. IBM provide this Qiskit tool, and so you can do a lot of. Similarly, Google has two tools. One is called Circuit that you can use. Another one you can also use. Right now they used. Um, Recently another tool that you can use for fault tolerant quantum computation. I forget the name actually, but if you search, the Google provide that those two things for you. And then interestingly, you if you're using in quantum machine learning and all those things, you can use a lot of penny lanes and all the type of tools that are all open source available. You can try all of them actually. I will if you ask me, I will suggest that start with IBM Qiskit, because IBM provides a lot of YouTube tutorials and all those things. There are a lot of courses available, and so over a period of time, IBM has developed a lot of free courses that are all available through YouTube. Previously, they used to open some summer schools also, and so but what is happening because of that? They have a lot of recorded lectures available, and they teach you just from the scratch that how to take a quantum gate, put on an IBM Qiskit, how to run a simulation, how to cascade them together. So in other words, consider that it's more like starting from the basics to the advanced concept, and you can do their exercises, and they also have tutorials and a lot of information available, because the reason is that I think in this case they have been developing this education material for a long time. So it is comparatively slightly mature. Even for some of my students who start, sometimes I ask them to look into those materials. They're pretty helpful actually.
Sir, continuing with this, so what is the library? Whether this library also free?
Which library?
This tool which requires to synthesize the
Yeah,
quantum topology.
yes. So actually, so as I told you right now, the Biscuit library is free. You can go to the it is available through GitHub. You can download it and run it. Okay. Some of the tools that we have developed right now, we have not released them actually, because we are still working on that. But the Biscuit tool that perform the approximate synthesis and all those things that is already available. You can go and download that actually. Okay, and you
So
can
is
run
there
it.
that means there is a standard library also, standard technology library for the quantum bits, qubits, or is there still development is going on this qubit standard library?
So there is no such standard library type of idea. You just standard set of gates. Okay. So there is standard set of gates, and then depending on, let's say, use IBM system, or use let's say IBM is a superconducting based system, or use different type of technology like ion trap or something like that. Then you can take an algorithm and develop a circuit for that and run it on their systems. So in other words, think in this case, how should I tell you? You consider that there is already like a standard cell library defined for you in a classical way. And when you take a standard cell library, then you cannot do too much from your side. You have to map those things finally to the standard cell. And sometimes they have the mapping tools available for you that can map those things to those set of gates for you.
So in that sense, sir, how we can compare with the work which was done by somebody and the topology you propose, and you have used some one library and other person are using some other, because there is no standardization in the library. So how to justify this comparison
Yeah.
in
So
terms
just
of complexity?
so justification of the from the complexity is coming from the algorithm side. Like for example, let's say if you let's say you propose a partitioning algorithm, right? Okay. So in the partitioning algorithms, you can easily come out with the compile time, runtime complexity, right? Okay. And the sole objective now, because both of the algorithms are available to you. Now, let's say you map it, and the mapping you can use the standard set of tools, and then later on, once you map it on the system, you can compare the error between those two algorithms, how much the error one algorithm is produced compared to the other algorithm, and that's how you can compare it.
So that is the
And
point of view partition and mapping.
yes,
And gate complexity and delay and all these things, how we can measure?
so the gate complexity and the delays you can also measure, because let's say once the partition comes, you can identify how many gates my each partition is seeing over a period of time. So you can write a program, and that can show to you, let's say when this first gate is encountered and when the last gate is encountered in that partition, how many gates you're encountering over a period of time. So it is very simple, because it's here in quantum computing, calculating delay is much more simple than a classical sense, because each of the operation is happening over a period of time. Okay. So you can use that method. Actually, you can say, okay, when I'm starting from here to the end, which of the gates I'm seeing over a period of time. So that is your depth.
So is this all this complexity, gate complexity and delay calculation can be done with the available tool, open source tool?
Yeah,
Or you have to do
some
manually, or some algorithm you have to write with some using the C programming or some other?
I think some of the thing you have to do it manually. You have to do it from the algorithm side. The tool is not going to do too much for you. Okay. Some of them they may give you some information. For example, right now, Google has developed a tool. Actually, just give me a minute. I will tell you the tool name. Actually, I'm just missing that tool name. Actually. Qualtron, yeah. So Google has developed a tool called Qualtron. In the Qualtron, let's say if you take an algorithm, you map it, it is going to give you a resource count, how many gate count it has, how many qubits it has, how many gates it has, what types of gate it has. The Qualtron does it, so it will give you the resource counts.
Mhm.
So
So one
Google,
question coming from the participant,
I will, I
same.
will, I will type it for everybody. So look into that. It's called
Is it
Qualtron.
enough to publish paper through those tools, sir?
Yeah, you can publish a lot of people. Most of the people are doing that actually.
Okay. And one more question from MG Rajendra Kumar, which one is the more significant, quantum or neuromorphic? Because I have also seen that lot of works is going on neuromorphic, and in the recently when VLSI conference, they are mostly focused on the neuromorphic also. So in that case, the new researcher who are joining the research program right now, they are starting their career. So how we can suggest to go with the which one way they can go, quantum or neuromorphic?
I think both fields are important. To be honest with you, it depends on your personal interest and the research interest. If you want to stick to the classical sense, then go for neuromorphic. Okay. But if you really want to go for the quantum type of ideas, because let's say if your objective is to work on classical computing paradigm, then go for neuromorphic. If you really want to try the quantum sense, you like more dealing with these types of new types of ideas and all those things, and then go for quantum. So I will say that it depends on the personal goals. But if you ask me, there are two different goals, right? One of them, some of the people who want to go for, let's say, industry jobs or academic jobs, right? Okay. So the question can come in that way. So I think this is a good time to work as an academician on the quantum computing, because there's a lot of things you can do in this area, right? So I will suggest that those who are looking for the research area, PhD problems, or want to become future faculties, then go for quantum. So go for quantum. Now you can do some analysis that if see right now, a lot of quantum companies are also opening up. So it might be possible that a lot of quantum companies are also hiring a lot of people. For example, can you in few years back, you would have never imagined that the companies which are working in finance domains are hiring quantum people, right? But nowadays, even working in the like the companies like I've seen that JP Morgan Chase or like Experian and other types of companies, now they're all looking into quantum for the financial type of application, right? Okay, so it depends on the personal goals. In my opinion, both areas are fine. For the researcher, I will say that you should do the research what you like today, whatever the topics you like, because in my opinion that when you're doing the whatever the topic you're doing, you're building a skill set, and the skill set could be transformed. I don't think, let's say, I won't say that I rather than I will say that this area is good, that area is bad. I will say all areas are good. It is all important that what skill set you're developing. And then once, let's say, once you become an academician or whatever, uh, if you have strong fundamentals, you can even go to the new topics over a period of time, right? And let's say, I feel that right now both neuromorphic is fine, quantum is fine. I feel that there will be job opportunities in both these areas. So I think this is the right time to work in any of these areas.
Sir, one more question in the that's how to validate it. Is there any functional validation device is available in the market, or it's like we can use the FPGA to develop such same topology to validate the functionality?
So people have looked into FPGA-based simulators also, but I will say that there are already, if you work for, let's say, IBM already have, you can download the Qiskit, and so you can use the simulators to test the idea, right? Sometimes you can also get like you can purchase the hours in those actual quantum machine and run the simulation. Okay, I'm pretty sure over a period of time, India is investing a lot of money on quantum systems. So I'm pretty sure that that they through some mechanism or through some grant, you can get access to the IBM machines and run simulation to the IBM machines. In our case, we get some access to the machines through some of our collaboration with national labs, and through that we sometimes run the simulation on the simulators, but we can also validate those on the actual machines.
So how we can access? Is there any chance that all the researchers for the world can across the world can access those simulators through some different way approach?
Yeah, so I will say that look into those companies' website, and I'm pretty sure that some of these companies may be set up in their offices in India and all those things, and maybe some of them are making it available to people all around the world, because I think the IBM kit and all those things are freely available to people anywhere in the world. But maybe the actual quantum computers may cost some money and all those things. So I will say that start with simulators to start with the research, because the simulators are really reasonable to start with, and even for them they put the noise model. So in other words, let's say let's say an actual quantum machine is there and it is noisy in nature, so they create noise model which you can put in the simulation, and it will give you some ideas that how your circuit is going to behave, which is good enough at least for the to start the research and publish papers and all those things.
Yeah, thank you. Anyone else? Do you have any questions? So you can drop or you can raise your hand. So one more question, sir, I have. So in recently, just post-quantum cryptography, because you are also working in hardware security. So in the post-quantum cryptography and quantum computing, how it is means we can see the architecture point of view. I'm talking about the architecture point of view.
See, the post quantum cryptography is also good, because right now there's a lot of work going on post quantum cryptography. Actually, one of my PhD student, he defended his PhD proposal today. His thesis was is actually on he looked into a lot of post quantum cryptography protocols for cyber physical system security, right? Because one of the interesting aspect, like post quantum cryptography, are mostly bulky in nature, right? Okay, because they are more number of the key size and all those things are slightly bigger. So you can look into hardware accelerators and all those things. How can you accelerate those things, right? Similarly, see how can you perform side channel attack on the post quantum cryptography, right? So that could be an interesting problem, like performing the side channel attacks. For example, you can perform electromagnetic attack or power analysis based side channel attacks on those cryptographic algorithms. Another interesting aspect that could be very much interesting, that how can you make sure, and there is already some libraries available into that, but you can come out with some new ideas. For example, let's say if you're working in embedded system domain, right? The embedded systems are microcontroller that is of 32 qubit or 16 qubits or something like that, right? Now, how will you make sure that a post-quantum cryptographic algorithms can be run on those type of systems, right? So that I feel that it's an interesting problem. Now, if you think you map it now, your system is algorithm, but you perform some side channel attack onto that one, right? So you can easily perform some side channel attack. Now the interesting problem could be how can you develop some side channel resilient solutions for doing that, right? Okay, so how can you do some resource optimized side channel resilient solution that can be applicable for the post quantum cryptographic solution? So those are all problems. There are a lot of researchers who are looking into these problems, and I think that is another interesting problem. And I
In
think
side channel attack, so you need to implement on the hardware. So you need to, let's say, a differential attack. Okay, in the differential attack, you need a power differential attack you are finding. So you need to analyze the power. So current and power. So how we can do it with for this post quantum cryptography?
so you can
Because right,
you can see there are a lot of papers which have, because there are a lot of papers which people have mapped them onto FPGAs, right? People have even developed some of the ASIC chips for doing that. So you can similarly you can map some of these ideas into FPGAs and perform a side channel, measure the power consumption and put an attack. Similarly, if you want to take a microcontroller, you can put a like a resource optimized version, and then you can measure the power consumption of the microcontroller and put an attack onto that one. So you have to map it to some hardware, either through ASIC, FPGA, or microcontroller, and then you can do that.
one question coming from Umar Farooq. How quantum computing is used in 6G or 7G wireless communication?
Actually, I don't work in that area, so you may have to look into the literature into doing that, because there may be some topics. But I'm pretty sure that quantum computing is used significantly in the communication by using. They are using actually there is, so you should look into that. Recently, one of the companies called INQ, they acquired a company called Qubitech, and that the sole idea was to they want to use quantum computing for communication purposes. And then you can search more details on the 6C. I personally don't work in that area, so I don't want to give you the wrong information.
One more question is coming from Subramanian. Whether cadence EDA tool are supported for quantum? Obviously, I think it is not there. Quantum computing simulation.
I will not say that, but if see, not for that purposes, but if you really want to simulate some of this control circuitry for quantum computing, right? So if you see, there's something called cryogenic computing, right? So that cryogenic computing, sometimes people want to use it for as a control circuitry, because when this quantum system are there, they need to have some control circuitry. Some of these ideas you can simulate in quantum, but I think not others actually, no.
Yeah, thank you, sir. I think, is there any questions? Control circuit, is it analog or digital? Some same part
I
is
think
asking.
mostly it is analog, and you can look into some work. They call it. You can say if you search, they call it cryogenic CMOS based control circuitry for quantum. So you will there are a few papers. You will find it actually the whole circuitry. It consists of couple of analog components. Converting them to digital world itself is possible, but if you see, most of them still talk about the analog world. So there are papers actually, you can easily find it on that one. There are a couple of groups working from the Europe side. I forget the professor name, but there are a couple of groups from the Europe side, and you will see that you will able to find those papers there.
Is there any questions from participant? Okay, I think there is no questions. Uh,
Okay, so I think
So you can reach out if you don't have any questions. So you can reach out with Professor Himanshu. He is available through his mail ID. You can note down the mail ID he has said in the
yeah,
initial.
yeah. So as I told you, better connect with LinkedIn actually, because the mails, so many emails we receive, and so if you have any question, you can ask me there. Okay, take care.
Yeah, thank you, Professor Himanshu, for delivering an exceptional session on quantum computing circuit and design automation. You are in depth discussion on quantum approximate synthesis, along with the design of analysis of various quantum adders, approximate adders, like ripple carrier or some other. So really, it was technically enriching. Your exploration of advanced techniques such as mapping with Saver tool or partition with QCEP tool, and partition expansion with the Leap offered valuable insight into the practical implementation challenges and solution in quantum computing. So on behalf of ATAL FDP team and all participants, we extend our heartful gratitude for sharing your expertise and providing us with a session that was both intellectual and stimulating and forward-looking. So thank you, sir. Thank you very much.
Thank you very much.
Participant, there is one announcement. You can join the one more exciting session at 2 p.m. It is FPGA-based accelerating biomedical signal processing. So you can also join the session at 2, and it is delivered by Professor Rajesh Kumar Tripathi. Thank you, everyone.